Sound check. We're good. Okay, so let's start off with a scenario here. This is actually a really common concept that you guys will be given on the diploma. Okay, they're going to give you a scenario. You have to interpret the scenario and merge multiple formulas together. This is what I was talking with you about a few minutes ago, where what we're going to have is balancing forces. Here's the scenario. You've got a scale. Okay, just a general, like, put something on the scale, it weighs something. You guys ever wonder how a scale works? Here's how it works. There is a wire inside the scale, and this wire is hooked up to like a kind of a box right here, and the wire's inside a magnetic field. As you run electricity through the magnetic field, it makes the wire get pushed up. Remember that one like lab experiment we did there where the wire moved when we turned on the electricity? The force of the magnet, that this is an Fm inside here, the magnetic force forces it up. Why is it getting forced up? Well, because gravity is pushing it back down. And that's actually how it's able to calculate a mass. That's what we're going to do here. We're going to try to figure out how heavy the object on the scale is so that the scale can read a certain value. So I'm sorry that I'm a little bit like, I'm going to have to flip back and forth between pages here. But here's our scenario. We're going to make a magnetic force equal to the force of gravity. This is not a formula on your formula sheet. Okay. One thing that I'm kind of discovering, being new to the school and how you learn physics, is that Physics 20, it sounds like to most of you guys, was just like a one formula sort of thing, where they gave you one formula, rearrange that one formula. If you get that in Physics 30, like, wow, that'd be pretty rare, because most of the time what we're doing is we're merging formulas together. This is going to be the formula I, L, B, and this is going to be mg. I'm going to merge two force formulas with each other. Does that make sense? Okay. So that's the difference. I'm still manipulating formulas, but rather than it being a formula directly off your formula sheet, now it's like you got to make your own formulas up. Magnetic force is pushing you up, gravity is pushing you down. Now, the good news is we have a wire length, so that's your L. We have a millitesla magnetic field, that's B, and we have a milliamp current. So like we have almost all the values we need. So let me start throwing them in the formula here. The length was 30 centimeters, so this length will be 30 times 10 to the minus 2, that's a centimeter. The current was also given to us, so again, sorry I'm flipping back and forth. Current was, is that 78 milliamps? Yeah, 78 milliamps. So 78 milliamps, 78 will have to go to the minus 3, I guess, to make it a milli. This B value right here for magnetic field, it was 3.75 milliteslas. Okay, so how do I do a milli? Minus 3 again? And we know gravitational field strength, 9.81. Okay. So all we have to do now is to solve for the mass, and that's actually how a scale does. A scale will have a little microcomputer processor in there that will basically record how much current is required out of the battery or out of the, I don't know, out of the AC out of the wall, and it'll record how much current it has to make the wire push up on whatever you're pushing down with, and that's how we figure out the mass. So I was dumb, I didn't bring my calculator, but I can walk through the middle now. This is better. I hope I don't come off as being condescending here, but I hope that this last step, you guys can all handle the last step here of just doing the math part. It's the getting to that step. That's usually the hard part. So what is it? 78 e minus 3 times 30 e minus 2 times 3.75 e minus 3. Divide by 9.81. Anybody else get this number? I got 8.944 e minus 6. Nope, not with you. Let me check. You did? Oh, maybe you're the one that has it wrong then. Sorry. 8.944 e minus 6. Oh, okay. Everybody else got that then? Negative 6. You have to the negative 11? You have negative 6. Okay, check yours one more time then maybe. So I guess this would be 8.94 micrograms, I guess. No, that's not right, actually. Hang on. Because minus 6, this is supposed to come in kilograms. So I guess why don't we just call it 8.9. How many sig digs do we get? 2. 8.9 times 10 to the minus 6 kilograms. So if I wanted to change the units, I guess, I don't know if this makes sense, but if I wanted to convert it to grams, then it would be 8.9 E minus 3 grams, which would then make it 8.9 milligrams, if that kind of makes sense. I'm just hopping down by factors of 3. So, but I'm sure we could just leave it this way here because we normally measure things in kilograms. Were you able to troubleshoot whatever was wrong there? Do you still get minus 11 or do you get minus 6 now? You're trying it. Okay. Anybody else have any issues? You got it to work? Else is good. Big picture concept-wise, were you able to figure out like how to merge these formulas together? Okay. I cannot tell you what they're going to test you on the diploma. They don't show me. I have 10 years experience, so I know what they've done in the past. I try to give you those examples on quizzes, but like to some degree, it's kind of a guessing game, right? I even gave you guys an example before on a slide where what they're probably going to do is make the magnetic force either equal to gravity or possibly equal to a centripetal force or possibly equal to an electric force. And like those are the 4 main forces that like somehow you're going to make like equivalent to each other. And you may end up having a formula where QVB equals mv squared over r. Or you may have a formula where mg equals, what's the electric force formula again? You have a formula sheet nearby? Let's do your formula sheet. I'm just trying to remember what the formula for Fe would be. Let's go with, how about E times Q? Here, that's a good one. For anyone who's done their first assignment, no, not first assignment, first activity, that's the one you're working on right now, right? This, when you make mg equals EQ, this is known as the Millikan experiment, for anyone who hasn't gotten to that point yet. It's actually how Millikan discovered what Q is. So, anyways, did you guys solve the exponent issue yet? Okay. Any other questions? Okay. So let's talk about a bit of review here as to some of the things we've learned. Like I said, today's kind of a hodgepodge. I've actually covered pretty much all the big concepts I need to. I need to give you time to practice them through all the labs and activities and stuff. So here's a bit of review. Here's Ørsted's contributions. This is actually one of the questions on your activity from yesterday. Here's what Ørsted discovered. Fellas, if you have a wire, and in that wire you have a current running, there's actually a magnetic field running around it. We didn't test this one yesterday, by the way. I didn't have the ability to do that. If you're wondering why, one of the reasons is that in order to detect a magnetic force, you need current times the length of a wire times a magnetic field. In order for it to be enough for us to notice it, we would have to have a decent amount of current. Current is what kills you. Like, did anybody touch an exposed wire yesterday? You didn't get electrocuted because the current that runs through that that black power source is pretty low. So like maybe you'll get a little bit of a zap, but like in order for us to actually notice it, I would have to use a considerable amount of current, and that's just not safe. So I wasn't able to demonstrate this one to you, but hopefully you get the idea, is that using that first thumb rule, that tells you how the field goes around. Okay. The one I was able to show you is the solenoid. That's where you have like a core. If you have a core and you wrap a wire around it, depending on the way that the wrap works, depends on which side is north and south. If you wrap it this way versus wrapping it this way, hopefully you can kind of see how there's a difference in the way I wrapped this one. This one went over and around, and this one went over the back side and down the front. Right? Depending on which way the coil is wrapped, depends on which way is north and south. That's the second rule. And then the third rule is the one where if you have like a particle going in a magnetic field, it can actually start to like bend and start going like in a circle. And that was the one where I had the horseshoe magnet. And there was like a wire running through it. And hopefully the wire like moved a certain direction. It was a little bit, right? The only reason it moved a little bit is it's that same formula, ILB. the amount of current we had was very minimal. It was enough for us to notice just a slight amount of force. Okay, so, anyways, that's the review. That's our main rules. There are some interesting applications that I need to talk to you guys about. So here's some like sidebars. This is like the random bits. A guy named Andre Ampere was messing around with multiple wires. As a side note, did anybody ever try putting two compasses next to each other? Sometimes you can get two compasses to interact with each other, because really, what is a compass? It's a small magnet. You put two compasses near each other, you can actually make them line up with each other. Well, a similar concept Ampere discovered with wires. If we have wires that create magnetic fields, if you have two wires next to each other, we can actually have wires that attract each other. It's small and it's subtle, and we don't really notice it unless you're carrying a huge amount of current or you have lots of wires. The only example I've ever heard of where this is a huge problem is an airplane. He said this can be a problem on an airplane because you can actually have wires that either attract or repel each other. Let me try to explain why here with this picture. Imagine that you have a wire that has the current going into the page. Remember how X means going into the page? Take your left hand, put your thumb into the page, and it means that the magnetic field is going clockwise like this. Okay. Now do it a second time right here. It's still going clockwise. Right. Now on this spot right here, the field is going up. Right. But if you have another wire directly next to it, on its right, on the right, it's going up, right? But if you have another wire right next to it, now it's on the left. That's the left, sorry. On the left, the field is going down. And you know what ends up happening is if you have a north-south field this way and a north-south field this way, can you guys see how those would want to attract each other? And so these two wires would actually be attracted to each other, which normally isn't a bad thing. However, what happens if you had something that was coming into the page and something that was coming out of the page? Can you guys see how this would cause a north-south attraction and a north-south in the same way? This would cause them to repel. Well, imagine you're an airplane and you have some wiring, and for whatever reason there's two wires and the current is going opposite directions. I don't know why it would be, but let's say it was, right? And there was enough current running through it that those wires started to separate. And all of a sudden, as the wires separate, a connection comes loose. And all of a sudden, you can't have landing apparatus come out underneath anymore, right? That would be horrible in an airplane. In your stereo system, probably not a big deal. Does that make sense? But we've got to be aware of it. So this is known as Ampere's law. Okay. All you need to know about Ampere's law is just that there's this concept behind it about how wires can actually attract each other or repel each other. So here's the factors: the length of the wire, the distance of the wire, and the current between them. Which probably makes sense because what's the formula for force? L, I, L, B, right? The magnetic field is going to depend on how much current you have. It's going to depend on how long they are. And honestly, if you had one wire over here and one wire over here, that's not going to do anything, right? But if they were super close to each other, yeah, that would make a difference. So, like I said, today's kind of like a random leftovers day. That make sense? Cool. Okay, another thing you need to know about. This is also a question on one of your activities. I want you guys to know how motors work. Okay. I want to try to get one from one of the teachers that have one in their room, but I didn't have time today, so I'll try to demonstrate this to you guys later. But a motor actually runs on the exact same concept, and I'm going to go to the front of the room to try to describe this, because this one's tricky. Hopefully the foosball table can be out of the way. Okay. Imagine that what you've got here is there's a magnet. There's a magnetic field sitting here. Let's say it goes north to south. Okay. As I need to use my hand rule, which way do we point towards? Towards the north or towards the south with our fingers? Towards the south. So my hand is going to look like this in some sort of orientation. Does that make sense? Now I'm going to talk about electrons. A motor is going to be hooked up to a battery. And so this battery right here, this is the negative pole of the battery. This is the positive pole of the battery. So electrons are going to run through here, through this wire. Sorry, maybe I'm seeing that wrong. It says the current's going this way here, but maybe that's the conventional current. Maybe I should use my right hand, I guess. I should use my right hand, I think. Because see how it says current here? I bet you they're meaning conventional current. So let's use my right hand, actually. Still going to put my right hand towards south, and the electrons are, well, not the electrons, but positive charges going this way here. Okay. If my thumb is going like this into the page, and my fingers are going that way, can you guys see how my palm would force the wire downwards? this wire right here is going to get forced down. You guys kind of interpret that? Thumb going into the page, pointing towards south. This wire is going to get forced down. UV. Because that's this part of the wire here. I'm getting to that one next. So then let's say the electrons keep going through the wire, they flip around and they come back again. Now my hand is a little bit different here. I'm still pointing my fingers this way, but you see my thumb's now coming out of the page? So this part of the wire right here, my thumb's coming out of the page, still pointing that way. This part of the wire gets forced down. This part of the wire gets forced up. And you know what you get? Torque. And it starts to spin. What does a motor do? Spins. Does that make sense? So that's basically the concept, is that you need a looped wire so that the electrons going one way get pulled down, and then the electrons that come back the other way, they get forced up, and it starts the spinning motion. Okay. So in terms of vocabulary, the words we use are stator, armature, and commutator ring. Okay. The stator is the two magnets. You have to have a magnetic field, otherwise this won't work. You have to have an armature. That's this coil of wire. It has to be in a loop. Okay? If this thing does not come back on itself, it would just move the one wire up, and that's all it would do. But you need this wire going down and this wire going up to start your rotation. Okay. The last thing you need is this commutator ring, and this will make more sense if I show you a motor sometime later, but there has to be a bit of a split in it. And the reason why is that if you start to force one wire down and one wire up, it'll go to here and it'll stop. And then it would just get stuck there, and so it would just do a 90-degree rotation and stop. What this split does here is it turns off the electricity for a split second so that its natural rotation can keep going, and then it re-picks it up and it re-torques it. The best example I've ever seen for this is like trying to turn like a big valve. Imagine that there's like a big wheel and I have to keep rotating it. So I try rotating it to here. I'd have to let go and re-turn the wheel. Does that make sense? That's what this split does right here. What would happen otherwise is you'd turn it that far and then it would stop, but if you cut the electricity off with a little split in the middle, then you can re-grab it again later. So that's a motor. In theory, you guys learned this in grade 9, because I've taught grade 9 science before, so maybe you've heard that at some point. Fellas. Did that make sense? Kind of? Okay, I'll try to show you a demo of a motor to help solidify that. So here's that same picture. Let me do the same thing now though, but I'll do it from the board here. I'll write on top of it. This one here, let's use our left hand this time. Electrons are going to be going through this wire like this, through that wire there, around the loop, and back again. Okay. Use your left hand this time, because we'll talk about electron flow. Point your fingers towards the south pole, and stick your finger kind of into the page, if you can see how I'm doing mine, where my hand, if I'm drawing it, this is my thumb right here, this is my second finger, this is my hand kind of like this, with my thumb pointing this way, this pointing towards the south pole. Which way is this wire right here going to get forced? Up. And by that same logic, as the electrons go around the loop, this half of the wire gets forced down. That's the torque required to get it starting to move. And that's why a motor can then make your tires move in a circle or whatever, right? Okay. Here's another picture of it, but I mean, it's the same thing every time. So the 3 parts you need to know: there needs to be a split in the ring so that it can continue going. There needs to be a permanent magnet, and there has to be a loop of wire. All right, moving on. Here's another thing that we can talk about. This thing's called a galvanometer. A galvanometer would be any sort of apparatus that has a little needle like this that rotates a little bit, if that makes sense. When you guys used a machine yesterday to measure whether there was current running through it, that would be like a galvanometer, where there's this little needle that makes a measurement, right? And in its standard spot, the needle goes here, but the needle can move from here to here to here to here, right? So the question is, well, why is it doing that? Well, this has to do with a similar sort of concept. What's going on is you've got the same sort of this magnetic field going on here, and as some current runs through it, and it goes from the negative pole through this wire here, however this works, to the positive pole, it ends up causing this thing right here to rotate. And as it rotates, it causes the needle to move. We can actually do some calculations based on this. So I've actually got a question on the next slide that's based on this concept. So let's try a math question. We've got a galvanometer with a wire of 3.8 centimeters, and I'm going to give you some new values. I'm going to give you a spring with a spring constant. If I go back right here, in a way, this little like curly thing right here is like a spring, right? And it wants to snap back to its original location right here. But what's happening is it's being forced like to rotate, right? So there's a throwback here. I've been discussing that we can have magnetic force equaling either gravity or centripetal or electric. But you know what else it can also equal? Is the spring force, which you would have done way back in like physics 20. Anything on your formula sheet is fair game, which kind of stinks because you have to be ready for like anything even from physics 20 still. Can anybody find me on the formula sheet the formula that like helps you figure out like a spring force? Is it S they use? Fs? It is negative kx. Do you guys recall this? I know I didn't teach it to you, but is this like buried somewhere in the recesses of your mind? You've seen this formula before? So there is a spring that is trying to keep the little needle from moving, and the magnetic force is forcing it against the spring, right? So we're going to make a new formula. Fm is going to equal Fs, and if I can kind of maybe draw it up here, based on the information I have, let's make it current times length times magnetic field. There. Now I've put myself together a formula. I don't know who taught you guys last year. The way I teach my students is I tell them to ignore the negative sign. I don't know what you were taught, but like I know there's a negative sign in the formula. The only reason why there's a negative is that you have to like pull back to make a spring work, and then the force actually goes the opposite direction. But like we don't really need the negative in this formula. That doesn't really apply. So hopefully that kind of makes sense. So anyways, throw in the numbers. This number here and this number here are both distances though. Make sure you get them in the right spots. So this is the 3.8 centimeters. Oh, and that's not right. Hang on. Delete that. This is the 3.8 centimeters. The spring constant was the 87.6. The 3.5 millimeters, that's how far you were able to move the spring. Right? The spring was only able to move 3.5 e minus 3. The Teslas is 1.25. And again, I hope I don't come off as being like cruel in any way here, but like at this point here, you got to be able to just math this now, right? Like multiply and divide, you're good to go. The hard part is like interpreting the scenario and making your own formula, because there is no formula on your data sheet that looks like this. And it may be the only time you ever see that put together. So anyways, 87.6 times by 3.5 times 10 to the minus 3 divided by 3.8 10 to the minus 2 divided by 125. I got 6.45. You haven't finished yet? I got 6 point, I guess I got 2 sig digs. I got 6.5 newtons. Anybody else? You did? Okay, that's a good sign. Yeah, so 6.5 with sig digs. So again, one of the things that I'm trying to prep you for, because I know that diploma exam is really going to be big in your mind, is that I don't know what scenario they're going to give you. I can promise you they're going to give you a magnetic field equaling something else. I said that wrong. A magnetic force equaling something else. And I don't know what it's going to equal. FC, FM, FB, no, FG, FE, right? But they're going to give you some sort of scenario. You've got to find a way to interpret which one is which. You got to make yourself your own formula. Once you make the formula, though, hopefully you guys will agree. Once I got to this step right here, you just plug all the numbers in. Any questions or issues on that one? Yeah, oh, sorry, we're solving for current, aren't we? Thank you. Sorry, I wrote F right here, so I was thinking it was newtons. We were solving for current, weren't we? So this would be amps. Thank you. My bad. Good catch. Sorry, we were solving for I. This is not work I was doing anymore. Okay. Here's another random tidbit then. Like I said, today's kind of the leftovers day. Another scientist I need you guys to know about, and be aware they will assess you on your scientists. Okay. I can remember the first year I taught physics. This was 2007. And I still feel bad to this day because I didn't prep my kids for the diploma well enough. And so I've taken the lesson to heart. They gave a question. It was like this. It was numeric response. So I'll see whether I can redesign it. I wish I could have prepped my kids better. They gave a list of names. So they gave like person 1. I'll just say person 1, person 2, person 3. They gave a bunch of different people. Okay. And then they gave some theories in the next column. So these were people. These were theories. And so, I don't know, like for example, one of them could be Rutherford. You guys know how Rutherford had the planetary model? Anyone ever heard of that before? Okay. Anyways, here was their question. It was 3 boxes. They said, pick a scientist. No, they said, pick a theory, pick a scientist who made a new theory. That was their question. They said, pick any theory you want off of this list right here. And then give me a scientist who came after them who had a new theory. I felt really bad after that year because like I didn't prep my kids nearly well enough for that. So I'm going to give you guys a heads up right now. They will test you. They could test you on what scientists did what and when. So because that was a pretty cruel question. You kind of have to know the time frame. Now you don't need to memorize necessarily like specific dates, but like you should know that Einstein came after Newton. Does that make sense? Like you should know the rough time frame of things. Yeah. So anyways. Okay, so anyways, since I'm talking about scientists here, Michael Faraday, we're talking a little bit later. So Faraday comes after Ørsted, okay, in terms of where we're at. Faraday was messing around with these things right here. This is called an induction ring. And you guys were kind of using this in the activity the other day, but it was a different setup. Here's what Faraday was trying to do. Faraday was trying to make it so that if he hooked up a battery and a coil over here, that coil over here would cause some voltage, some current over here. That's what he was trying to do. Basically, a battery over here would cause this device to run. And as you can see in this picture right here, what ended up happening was it didn't. Okay? Because this iron ring didn't conduct electricity. Okay? What ended up happening was this thing right here, the electricity went through here and completed a circuit there. This thing did not conduct electricity, and so even though there was a ring over here, there was no current set through there. But here's what he did notice. When he opened the switch, the ammeter did work a little bit, just temporarily. And when he closed the switch, it changed a little bit. And you guys did something really similar to this, where you had like a coiled ring, and you put a magnet into it. And only when you put the magnet in did you notice this little needle right here moved a little bit. Is that what you guys hopefully noticed the other day? But it was only when you moved it in or out that something actually occurred. And that's kind of what Faraday was discovering here in his example, is that what would happen here as you make the switch go on? As you make the switch go on, I don't want to bother figuring out which way the field is, but let's pretend this makes this north and south. Does that make sense? Well, if that makes this north and south right here, maybe what was happening is it was inducing a north and south right here. And as soon as the north and south right here was induced, it actually caused the electrons to move through the wire just a little bit, but only as soon as the switch was turned on. As soon as the switch was on, the field was now there, and it stayed there. As soon as you turned the field off, this all of a sudden stopped, which then affected this field, which then affected the electrons. So it was all about like when you turned it on and off, or in your guys' example, it was only when you moved the thing in or out. If you took the magnet and put the magnet inside and just left it there, nothing happened. It was only when you moved it. And so that's what Faraday discovered. The term we use for this is called electromagnetic induction. So like in the theory that they could possibly ask this question, if they do, his theory would have been electromagnetic induction, and that came from Faraday. Anyways, here's the concept. I want to try to describe it a little bit better. I don't do this often. I'm going to read right out of my notes. Faraday had hoped that the current would flow through the iron ring and be detected by his ammeter. But when he ran steady current, nothing happened. Okay. So like when he closes this switch here, the electrons run through this wire, and nothing happened whatsoever. There was no current over here. But he did notice the needle of the ammeter moved when he turned the switch on and off. Here's what was happening. The apparatus was creating an electromagnet when he turned on the current. This became a magnet where this was north, this was south. That induced a magnet field over here. And so it went from having no magnet to having a magnet. How is that different than there's no magnet inside here to now you've shoved a magnet inside? Does that make sense? As soon as a magnetic field turned on and changed, it made electricity. So the first electromagnet induced a magnetic field in a second electromagnet, and then that is what caused a little bit of voltage or current to be discovered. So the word we use there is actually the word induction, induced. It's very similar to electrostatics, but you'll have that word come up more than once, induced. So here's the basic concept. They concluded that when a piece of wire and a magnetic field move relative to each other, they can make electricity. Going back to the picture here, when you made this bar magnet move into this field, you made electricity. When you stopped moving, the electricity stopped. One of your post-lab questions was to research AC, DC, and not the band. Anybody done that so far? Okay, let me give you the cliff notes. DC stands for direct current. When you put the magnet in to the coil, it causes the electrons to go like this way through the loop. And that causes the meter to go like that way. Now, that's direct current, going one direction. You guys know what AC stands for, right? Alternating current. Maybe you see where I'm going with this. If you take the magnet and you put it in and out, and in and out, and in and out, and in and out, that's alternating current. Because the electrons are basically, they're going forwards and then backwards, and then forwards and then backwards, and forwards and backwards. That's alternating current. Exactly. Which leads me to my next topic, which isn't actually in my notes here, but I'm going to go back to the motor. One of the other questions I'm going to ask you at some point is, what is the difference between a motor and a generator? A motor versus a generator. I'm going to go back to the board here, and I'm going to go back to a picture of a motor here, which was this guy right here. What does a motor do? A motor takes a battery and causes the electrons to go through the battery. When the electrons then go through the field, it causes motion. That's a motor. You take electricity, you make motion. You know what a generator does? It's the opposite. A generator takes motion and causes you to store up electricity. You can actually do the opposite here. If I were to take this thing right here and I were to put it on a crank and crank it around in circles, that would actually cause AC current. Because if I move the wire, if I physically move it, it'll actually cause the electrons to run backwards. You can either have electricity causing motion, or you can cause the motion and it'll provide the electric charge. And that's what you guys would have seen when you guys did the, when you guys moved your bar magnet into the generator like this. By you guys forcing it into the wire there, you created electricity. That is a generator. Does that make sense at all? Okay. In order to figure that out, that's what I think I have these slides here. You just need to remind yourself about how this concept works. Say you have a wire. So this is a piece of wire right here, only I'm going to loop it all the way around. Okay. And I'm going to take this wire and I am going to move it in the field, like around the magnets. So this wire is going right here, and I'm going to move the wire up. So let's say I move this wire up here. You see how this guy's thumb is pointing in the up direction? So because you're going to lift this wire and lift the wire up. The thumb's going up. The fingers are pointing towards the South Pole right here. Can you envision with your left hand how your palm is facing towards you? Well, that is going to then create a force. Now, since you are the one moving the wire, you know what ends up getting forced is the electrons. And the electrons, they get forced around the wire, making electricity. So if you were to take this wire and pull it up, you'd make electricity. Or maybe you don't move the wire. Maybe you take the magnet and you move the magnet down. Either would really work. You could either move your magnet or move your wire, but it's the same rule. This is the direction of motion. The V is the motion. The palm is the force, and then B is still your field. So if you move this wire up, it would actually force the electrons around this way here. So let's try a little kind of example here. Let's say that I gave you a magnetic field, and I gave you a wire, and I told you that you were going to push the wire down. Which way will the electrons go? You got a 50-50 shot at this. They're either going this way or this way. Okay. So let's try our hand rule. I'll go stand at the front of the room again here. What do the X's mean? Okay, so your hand's facing into the board. Okay. Then the force is going to be like the direction of motion is your thumb. So I'm going to make my thumb go down like this because I am moving the wire down. Sorry. So I am moving the wire down. So fingers into the board, thumb down. Which way do the electrons get pushed? This way towards the left. Does that make sense? So if you push the wire down, you'd make electricity that would go to the left. If you push the wire up, the electricity would go to the right. Okay? So if you basically took this wire and kept moving it up and down and up and down and up and down and up and down, you've now made yourself alternating current. Okay? Which is what a generator does. Right? If you know much about generators, like take a generic hydropower waterfall, right? What you end up having on a hydroelectric dam is you have a river, and the river has like some sort of dam that's been built in the way, right? And it wants to like fall down, but the water can like leak through the dam. And what it does is it spins something around in a circle like some sort of turbine, and the spinning of that turbine causes this wire to go up and down and up and down and up and down. And as it does it, it makes electricity. It's absolutely brilliant, actually. If you were to ask me to put together my top 10 list of like the most important scientific discoveries, electromagnetic induction is probably in my top 3. Just because like it's what gives us our electricity. We would literally be like working with candles, and like we need this for our electricity. Okay, we're almost done. The next guy I need you to know about is Heinrich Lenz, and he started thinking about how would this apply if you took a magnet and threw it inside the coiled wire. He wanted to figure out which way are the electrons going through like the coiled wire. Okay. And he realized that there's only 2 possibilities. If you take a magnet and shove it inside of a wire, either it's going to be a south-north orientation, which means the electrons would go this way around the wire, or it would be a north-south orientation, meaning the electrons are going that way around the wire. He just wanted to figure out which way are the electrons going, left or right. Now, when it was a straight piece of wire, that's what this example was right here. But we're now talking about what happens when you have the coil of wire. Okay? And so he figured it's got to be one of the 2. Okay? He discovered that it always opposes motion. It's kind of like Newton's third law. You know how Newton's third law is for every action there's an equal and opposite reaction? If you're going to throw a north magnet in to a solenoid, what's going to end up happening is it's going to induce an opposite. It's going to induce a north. So that if 2 norths try to oppose each other, what you're really doing is you're creating a magnet so that instead of it being a magnet, it forces the electrons through the wire instead. So if you want to figure out which of these 2 it is, I'm going to go back to this slide here. If you want to figure out whether the electrons are going up this way or down this way, the right answer is the bottom one. Put the magnet in, north is going to induce north, And what that's going to do then is that's going to cause me to put my hand like this, because your thumb points towards the north, right? And then the wires are going to go like this, and I'm grabbing the wires this way, so the electrons are coming on the downswing of the wrap. That's how you figure it out. So now the way that we did this in the lab the other day, you guys remember putting that little magnet through the tube? Did you discover that like the magnet fell a little bit slower? The reason why the magnet fell slower in our tube the other day is it was doing the exact same thing. It was inducing its own magnetic field in the tube. You have your copper tube here. Sorry, I'm in some of your way. Okay. And as you put your magnet in the tube, this north-south right here, what it did is it opposed the motion by causing the tube itself become slightly magnetic. And what ends up happening is that as this north tries to go into there, it gets pushed back up. And so although gravity's pulling it down, a magnetic force was actually trying to prevent it from going down. And so the magnet should have fell a little bit slower, hopefully. So this is Lenz's law. Basically, this is the thing you need to know. It's going to oppose the motion. If you put a north magnet in, it induces a north going that way. If you were to have the exact same thing here, and you were to pull this out, let's try to answer my last question then. Which way will the current flow? Is the current going to go around this way in red, or is it going to go down this way in blue? So let's give it a try here. First question, if you're going to pull the north magnet out, what sort of pole is going to be created here, a north or a south pole? A south pole. Because if you try to push in, it'll oppose it. If you try to pull it out, it also wants to oppose. How do you oppose a north magnet getting pulled out? Put a south magnet here, right? Because doesn't a south want to attract a north? Okay. So then, now that I know which way the induced magnetic field was, I know that my thumb is going this way. So now you got to figure out which wrap makes more sense. As I grab this like this, is this the blue orientation or the red? And it's like, this is hard to like visualize sometimes. But like, as I grab with my thumb this way, do you feel like the electrons are going with the red going up or the blue going down? And hopefully you can see it's the red. Because as I'm putting my thumb finger towards the north here, my fingers are these up arrows of red here, right? My fingers are going up on the front side. If they were coming down around the back side, that would be the blue ones here, but then my finger would be pointing the other way. So the right answer to this one is in red. This is the direction the current would be flowing. It would be going from here, and finishing there. So one more time. This has to oppose each other to go out. So that means that this is south, this is north, my thumb points north. Then you got to figure out, is it going over the top like this or around the back like this? And if my thumb's going this way, it's going over the front like this. So that means it's coming up like this over there, up like this over there, up like this over there, up like this, and finishing. Okay. I'm gonna close that door. Shh. Okay. Does that make sense? If you need to, I can go grab some manipulatives and we can kind of try it, because it is tricky, like the spatial visual skills to be able to see that. Like if you don't get it the first time, don't freak out. Just keep coming at me until I can try to like explain it better. So that was our last slide, right? Okay, so let's do a quick summary of where we're at then. I'm not planning on starting our next unit for 2 more weeks. I'm done covering all of like the content in like a big group that I feel like I need to. Okay. But like you're gonna learn more by doing the assignments, by doing the quizzes, by doing the activities. So like to me that's where the learning comes in, by trying those things. Okay. Hopefully I've given you enough to get started, but like I expect that you're gonna ask me questions. Like that's how I designed this. I think you're gonna learn better that way. Okay. So approach the next 2 weeks like this. By next week Friday, finish everything that you possibly can. Okay. And if you need more time than that, that's fine. But the week after that, I'm going to start on a new unit. Okay. In that time frame, you should probably finish off your old quiz, your old activity, new quizzes, new activities, do some assignments along the way. and like you choose when to do stuff. Okay, I threw some due dates on the board over there just because some of you feel like you need due dates. I don't care, because like my only requirement is that if you don't finish it by my due date, it just has to count for a mark. Okay, so sometimes I want you to think of like, is it just better for me just to do it, not stress over it being perfect, get some feedback from Chris, and just move on? You know? Or if you want to take like 4 weeks to do this, like you're only gonna fall behind though, right? I think a few of you already know that like, oh, you're digging a hole. Like sometimes just move on, right? Let's just take what we've got. Let's just start fresh. Does that make sense? So, I know we don't have a lot of time left today, but if you guys want to start working on assignment 2 or assignment 3, ask my questions. The answer keys are all on the board over there, so get feedback as you need to. So the only thing I'm going to do otherwise for the next 2 weeks is be here to help you, okay, because you need help. And then tomorrow we're going to do the lab, but I got to be honest, the lab is going to take us about 10 minutes to do. It's kind of like the, remember the duct tape cannon that I blew up in the hallway there? It's going to take 10 minutes to get the measurements. So that isn't going to take very long. The rest of it's going to take longer. We have to measure that. You know, we have to like analyze the numbers. So we're going to use Tracker software. Yeah. So I have laptops booked actually, because I felt like the computer lab didn't work all that well. So I'm going to try laptops, and I'm going to try to have you guys have the laptops right here with you in class so that I can try to help you out as we do it. So hopefully that makes it better. Okay, do you have any big picture questions as to how the rest of this unit is going to look? Does that part make sense? Okay. Do you guys have any questions about like content and stuff like that? Because I'll do that in smaller groups, I guess. So, okay, I'll stop my recording then. If you guys want to, you're free to go somewhere else. I'd recommend stick around.